Hello. So we had left off talking about Fourier series, and we had a discussion about divergence of Fourier series, the upshot of which was that a Fourier series generally diverges. So what we're going to look at now are conditions under which Fourier series does converge, first of all. And then later on, we'll look at different ways of inverting the CDFT, because remember that the Fourier series arose as a natural way to invert the CDFT. And although it's natural, it's not actually very good in a general sense. Okay, so the point is, what we want to do now is we want to give conditions under which Fourier series converge. All right. And so there's various kinds of convergence, as we know. And the first conditions we're going to give pertain to pointwise convergence. Okay, and so historically, these were the first kinds of convergence tests that were given. And the first of these was due to Dirichlet, and so we're going to state Dirichlet's condition here in a minute. And this was sort of in about, I forget, 1815, I think, or possibly a little bit later, but something in that nature. Okay. All right, so a crucial thing that we had from our previous discussion of Fourier series in general was that we had this formula for partial sums, and this is really the crucial fact about all discussions of convergence of Fourier series is starting with these partial sums. Okay, and the point is that there's this interesting formula that's attached to these, and it's this formula. Okay, where this thing is the Dirichlet kernel, and the Dirichlet kernel comes in sort of two different forms. One is kind of an explicit formula, which makes it look complicated, and then there's another definition of the Dirichlet kernel, which is often useful in practice. So I'm going to recall both of these here. And so the sort of explicit formula is like this. And then this is when t is not 0, and t is equal to 0. Okay. So that's sort of an explicit, oh, sorry, I apologize. So it's, okay. But in fact, sort of a simple way to view the Dirichlet kernel is that it's simply this sum. Okay, so and it turns out that those two formulas are the same. Okay, so we're going to make use of both of these right now. Because what we will state is what you might call the sort of fundamental theorem of pointwise convergence of Fourier series. And the result reads as follows. Okay, so first, we let f be in L1 per t periodic. Okay. And then what we're going to do is we're going to list a bunch of equivalent statements. And so the following are equivalent. Okay. All right, so the first statement is that the Fourier series at some point, and so I should say here, I'm going to fix the time t naught, okay, because I'm talking about pointwise convergence. And I'm going to fix some number, complex number s, and the idea is that s is the limit of the Fourier series at t naught. Okay, so the first statement is simply that the Fourier series converges pointwise at t naught to s. Okay, and so the remember the partial sums for the Fourier series we denoted by this symbol. Okay, and so the reason we denote the partial sums, so these are of course the partial sums, and the reason we use this notation as we talked about is that that's a convolution. Okay, all right, so that's just Fourier series converges pointwise at t naught to s. Okay, and then the remaining statements are statements which are equivalent to that. Okay, so the first statement is that the limit as n goes to infinity. Okay. So I'm just going to write these down, and then we'll see why they're true. Okay, so there's another condition, and so like I said, we'll see why these hold. All right. The third statement is quite similar to the second one, except we get to replace the upper and lower limits with arbitrarily small quantities. And so for any epsilon in 0 to 2, the limit as n goes to infinity, t, we go from now it's minus epsilon to epsilon, and then the rest of it is the same. Okay. And the next statement is sort of builds off this, and you have this explicit formula now for the Dirichlet kernel, and essentially what the next formula does is it replaces this with the sort of approximation for small t, that sine of theta is approximately theta. So for any epsilon 0 t over 2, and you can include t over 2 in there. Limit as n goes to infinity. So the details here are less important, so I'm not gonna. So integral from minus epsilon to epsilon. And so here what you get is you get f of t naught minus t minus s over t. Okay, so this t in the denominator here is like a substitute for the denominator of sine t there. And so we still need the numerator. Okay, so we have that. Sine 2n plus 1 pi t over t dt is equal to 0. Okay, so those are the four equivalent statements that we're going to work with, and we'll talk about how valuable these statements are and what they tell us and what they don't tell us. Okay, but first let's prove this. Parts of it are easy to give exact proofs for. Other parts of it we'll just kind of wave our hands a tiny bit. Okay, so let's first prove the equivalence of 1 and 2. Okay, and so what you see here is, all right, so we're going to go from this statement to this statement. Okay, and so remember that this is already a convolution, right? And so really what's going on here is you're taking the S over to this side and you're trying to squeeze it inside the integral. That's really what is happening there. And in order to justify that, you have to just do one, you have to make one elementary observation. And that elementary observation is this. So using, oops, using the definition. And so the definition is this, which I'll call star, star of the Dirichlet kernel. We directly compute, because it's just doing a simple integral now of complex exponentials. And so what's true is that 1 over t integral from minus t over 2 to t over 2 d per t and t dt is equal to 1. Okay, so again, that just follows directly from this representation of the Dirichlet kernel and doing the integral. All right, and so then the point is that you can directly pull this s over to this side, so it's minus s. Okay, so that's the minus s here, and then the integral of s, which is just a constant for our purposes here, times the Dirichlet kernel is equal to 1, and so therefore you can just pull it inside the integrand like that. Okay, all right. And so that proves the equivalence of 1 and 2. Okay, now the equivalence of 2 and 3. Okay. All right, so the idea here is, and we've seen this before when we talked about the injectivity of the CDFT and the Fourier kernel, is that these kernel functions have this character of, well, the Fourier kernel was a legitimate approximate identity, and so it has this behavior around 0 of, kind of, getting very spiky. So getting large at 0 and decreasing away from 0. And the Dirichlet kernel has a similar property, but we did see that the Dirichlet kernel is not an approximate identity, but nonetheless, its properties are enough to get this kind of focusing behavior around 0 instead of on the whole interval. Okay, so let's actually, because the Dirichlet kernel is not an approximate identity, you have to be a little bit careful about that. Okay, so so here's what you do. So we note that, oops. So we note that away from a neighborhood of 0, and so what I mean by that is on a domain that minus. Okay, so you take the one of the periods from minus t over 2 to t over 2, and you excise the little bit that contains the interval minus epsilon to epsilon. Okay, and then on that domain, you observe that this function f of t naught minus t minus s. Okay, so that's our thing inside the integrand here. And now I'm going to take the denominator of the Dirichlet kernel and pull it in here. So this is pi t over t. Okay. And so away from zero, okay, the denominator here is going to be bounded. F is in L1. Okay, so what do we have here? So the numerator is in L1, and the denominator is bounded, and so therefore this function, it's a product of something in L infinity with something in L1, and so the product of something in L infinity with something in L1 is in L1. Okay, and so the point is that that function is in L1 on a domain like that. Okay. So it's integrable. Okay, so then the thing that I'm looking at, so I know I'm working with the equivalence of 2 and 3. So in 2, I have this. Okay, and so what I'm going to do is I'm going to explicitly break out the Dirichlet kernel into its numerator and denominator, and so I have the denominator here. Okay, and so therefore, okay, so let's calculate, or not calculate, but look at what happens to the integral from minus t over 2 to positive t over 2 with the little segment around epsilon removed. Okay, so I'm going to have the integral from so I'll write it like this. Okay, so this is going to be the integral over the period from minus t over 2 to t over 2 with the little segment around 0 with 2 epsilon removed. Okay, so now it's f of t naught minus t minus s. Okay, so I have the Dirichlet kernel, and again, I'm going to break that out into its numerator and denominator. Okay, so that's the denominator, and this is the numerator. So, okay, and okay, and what if I can show that the limit as n goes to infinity of this thing is equal to 0, then that implies that the limit as n goes to infinity of this will be equal to the limit as n goes to infinity of this, because I've shown that the remainder bits, okay, so the bits from outside of minus epsilon to epsilon go to 0. Okay, so then what the question is, why does this integral as n goes to infinity, why does that go to 0? Okay, so the limit as n goes to infinity, I claim that this is equal to 0. And why is that? Well, what am I doing? I'm integrating a function which I just claimed was integrable, that's that thing, times a harmonic function, okay, a sine function in this case. Okay. And the frequency of the harmonic, which is 2n plus 1, and I don't know what you want to jumble in there as frequency, but the point is that the frequency goes to infinity as n goes to infinity, and so by the Riemann-Lebesgue lemma, that limit is equal to 0. Okay, so that limit is equal to 0 by Riemann-Lebesgue. Okay, so that's the equivalence of 2 and 3. And so here, the equivalence of 3 and 4. So it's not that difficult to make this precise. You just have to compare carefully, a little bit carefully, the difference between this and then the term with the denominator from the Dirichlet kernel in there, and then show that difference, the integral of that difference times this, and again, there's a Riemann-Lebesgue argument in there, but the point is sort of this holds since sine t t is approximately t over t for small t. That's the moral of it anyway. Okay. Okay, so that's sort of, like I said, the basic pointwise convergence theorem. Now, there's one thing about the theorem which is very interesting, and that is really in the equivalence between 2 and 3. Okay, and why is that especially interesting? Because it's interesting because it tells you that if you want to know the pointwise convergence of a Fourier series of a signal f at t naught, so take a look at the integrand here. So t here in the integral is going from minus epsilon to epsilon, and so this is really just the integrand on this interval only contains information about f in a neighborhood, an arbitrarily small neighborhood, but with a non-empty interior, a neighborhood of t naught. Okay, and so part 2 reflects the localization principle for Fourier series. Okay, why localization? It only requires information about f arbitrarily close to t naught. Okay, and so that's already an interesting thing, and there's not necessarily any reason why this should be true a priori, because you're talking about the convergence, pointwise convergence of a series. That series being the Fourier series, whose nth partial sum we denote here, and the coefficients in that series, okay, involve, all right, so this is the coefficients or the CDFT of f, the coefficients in that series involve the integral of f times harmonic functions over the entire domain, okay. And so you naturally might expect that the conditions for convergence of this series might depend on points t that are far away from t naught. Okay, but it's not true, and it has to do with again this kind of localization property of the Dirichlet kernel. So remember that I'll sort of just sketch it here roughly from minus t over 2 to t over 2. That the Dirichlet kernels get like this, and then they get very high, and then you get the oscillatory bits. Okay, so you get this kind of focusing behavior near a neighborhood of t naught, and that's sort of the crucial thing that makes this hold. Okay. All right, so that's an interesting thing about this result about pointwise convergence of Fourier series. Why isn't this result just the most awesome result in the world? Well, it's because the conditions really are not necessarily all that checkable, okay? Because they have to do with the integrals of f times some function, and so to test the conditions really is not a lot different than testing the it's really just almost a restatement of pointwise convergence, okay? And what you would like. So let me sort of say that the result is not very practical because it does not give easily checkable conditions on F for pointwise convergence. Okay. All right. So now, of course, I'm saying easily checkable, and one person's easily checkable, maybe another person's impossible to check. So I should be a little clearer about what that means, and I will do that by stating some practical pointwise convergence tests for Fourier series. Okay. All right, so we're going to give a couple of results, which give you some conditions that you can, for many signals F, will give you pointwise convergence for those signals. Okay, so let's do that. All right, so the first test we're going to look at is called Dini's test. In fact, all of the conditions we're going to look at are really simple consequences of Dini's test. And so Dini's test says this. Okay, so all of these conditions for pointwise convergence are going to require that F be in L1. Okay, so if F's not in L1, these tests do not apply. All right, and that's just very simple. F being in L1 is necessary and sufficient for the CDFT of F to exist, and therefore for its Fourier series even to make sense. Okay, so but you do have to watch for that, because sometimes you can have signals that are not in L1. Okay, good. Okay. Okay, so we're going to talk about, as we did in the theorem, pointwise convergence at T naught. Okay. So if there exists an epsilon positive and a complex number S, so that okay, so this numerator here we recognize from our basic pointwise convergence test. And then we also recognize this from the fourth of the conditions. But now what I'm going to do is I'm going to require that this integral be finite. And so what that really means is that the integrand is integrable on what's epsilon to epsilon. Okay, so if you can find an epsilon and an S, so that's true. Okay, then you have pointwise convergence at T naught to S. Okay, and so that just means that the limit then goes to infinity. These are again the partial sums of the Fourier series. Okay, all right, so this is a sufficient condition. All right, and it's easy to prove. We're going to use the fourth condition. And so it's the integral from minus epsilon f of T naught minus T. It's S over T sine 2 n plus 1 pi T dt. Okay. So we have hypothesized that this, on this domain, is integrable. right? That's the hypothesis of Dini's test. And so therefore, by Riemann-Lebesgue, because again, I'm taking the integrable function, multiplying it by harmonics whose frequencies go to infinity as n goes to infinity, and so that limit must equal 0 by Dini's test. Okay, and so then this just immediately follows. And so this is true by Riemann-Lebesgue. Okay, and that immediately gives Dini's test by part 4 of the previous theorem. Okay, so that's Dini's test. And so Dini's test has a simple and very useful corollary. Okay, so it says that if F is in L1 per, okay, and if F is differentiable at T naught, then the Fourier series at T naught converges pointwise, and moreover, it converges to F. Okay, so the limit as n goes to infinity of the partial sums of the Fourier series converge at T naught, converge to F at T naught. Okay, so that's nice, but and we'll see that when you talk about specific examples, most of the signals that you sort of encounter in life, they are very often differentiable in lots of different places. Typically, in the examples that we're going to see, they're differentiable except at sort of an isolated set of points. So for nice signals, this immediately gives you pointwise convergence on a large set. Okay. Okay, so let's see how this is proved. So since F is differentiable at T naught, okay, so the limit as T approaches the limit as T approaches T naught of F of T naught minus T minus F of T naught over T. So I've taken the usual differences for the derivative, the difference quotient for the derivative. I just changed things slightly. But the point is that this is bounded. Okay. All right. And so is bounded, or sorry, let me first say this. So this limit exists. And so therefore this thing is bounded near T naught. Okay, and then this immediately, if it's bounded near T naught, then certainly that thing will be integrable, and then you immediately get the result from Dini's test. So this thing will be integrable with S equal F of T naught is the point. Okay, so the result follows from Dini's test. Okay, so that's a useful condition. And then the next and last result that we'll talk about is the Dirichlet test. And the Dirichlet test requires us to look at a couple of limits. Okay, so let's write the limit as let's write f of t naught plus, okay, to be the limit. So it's the limit as epsilon decreases to 0 of f of t naught plus epsilon. Okay, this is just shorthand for that limit, and that limit may not exist, in which case f of t naught plus is not well defined. Okay, but we're going to look at a theorem where the hypotheses are that these limits we're about to define, they do exist. And similarly, you have the limit as f of t naught minus, which is the limit as epsilon again decreases to 0 of f of t naught minus epsilon. Okay, so this is the limit from the right, and this is the limit from the left. Okay, and you can also do this with derivatives. Okay, so this will be the limit as epsilon goes to 0 of, okay, so it will be the limit of the derivative from the right. Okay, so this will be f of t naught plus epsilon minus f of t naught over epsilon. Okay, so the difference quotient for values of the argument that are to the right of the point t naught. And then similarly, f prime of t naught minus is epsilon to 0. Okay, and you're going to get f of t naught minus epsilon minus f of t naught, that's minus epsilon. Okay, so the limit of the function from the right, function from the left, derivative from the right, derivative from the left, when those things exist. Okay. All right, and then the Dirichlet test. Is so if f is in L1 and if for t naught in R, the limits f of t naught plus, f of t naught minus, f of t prime of t naught plus, and prime of t naught minus exist, then, okay, the Fourier series converges pointwise at t naught. Okay, so, and the limit of the Fourier series, the pointwise limit at t naught, is the average of the limits of f from the left and the right. Okay. All right, and so it turns out that Dirichlet's test is actually a consequence of Dini's test. Okay. And it's just sort of direct computations, changes of variable, and things of that nature. Okay, good. So let's look at some examples to illustrate how you use these tests and why these tests are valuable. Okay, so before we start, let me just say a few words about why these tests are valuable. They have the benefit that all of the conditions, so just involve simple conditions on f, right? Integrability of this thing, differentiability, and then existence of these limits. Okay. And so the point is that these are in the category of easily checkable conditions on f. Okay, and so let's see exactly how they're easily checkable by looking at some examples. Sorry. Okay, so we had these two signals that we had talked about previously, sort of a square wave signal and a sawtooth signal. So we're going to use these as kind of our prototype examples to talk about convergence of Fourier series. So let me recall what these are now. Okay. All right, so this function, which we called f, took a value 1 from a 0 to a half, and then took the value -1 from a half to 1. And okay, so the thing is periodic, right? So its graph extends like so. Okay, so let's try to apply our previous tests. Okay, so let's try Dini's test. Okay, so Dini's test requires that, sorry, before we do that, sorry. All right, so first of all, and this is always the first step, and so obviously I often forget it, is you first look for places where you can apply the easy corollary. Okay, that if f is differentiable at t naught, then the Fourier series at t naught converges to f. Well, f is differentiable except at these points of discontinuity. Okay, so at all of these points, okay, in these open intervals from 0 to a half and a half to 1, the Fourier series converges to f. Okay, so at all points except points. Okay, so the points of discontinuity, but the points of discontinuity are points that look like integer multiples of a half. Okay. The Fourier series converges pointwise to f. Since f is differentiable at these points. All right. Good. So really what it means is we only need to focus on these points where f is not differentiable. Okay. All right, so at points where f is not differentiable, okay, we use our tests. Okay. So the first test we're going to use is Dini. Okay. And Dini's test requires, remember, that this integrand on some neighborhood around the point, and so let's maybe take t equals 0 for concreteness, and so we need to find an epsilon so that on the interval from -epsilon to epsilon, and we need also to find an s that this thing is integrable. Okay, so let's see if we can do that. Okay, all right, so we're going to take t naught equal 0. Okay, and we're going to choose an arbitrary epsilon and an arbitrary s, and see if it's possible to choose those things so that the thing we need to be integrable to apply Dini's test is integrable. Okay, so we need that the integral from minus epsilon to epsilon f of, okay, so it's f of t naught minus t, but t naught is 0, so f of minus t minus s over t dt should be bounded. Okay, so we're going to take the integral and we're going to break it into its 2 bits from minus epsilon 0. Okay, right, and so from minus epsilon to 0, t is negative, so minus t is positive, and so that means that the value of f is 1. Okay, so it's 1 minus s over t dt. Okay, and then the part from 0 to epsilon. Okay, and so now arguing similarly, but with t positive, so minus t is negative, you get minus 1 minus s over t dt. Okay. All right, so the question you want to ask is it possible to choose epsilon and s so that both of these integrals now, they both need to be finite. And the only way that they'll be finite, okay, so this thing is less than infinity, okay, so we're basically integrating here a constant, namely the constant 1 minus s times 1 over t, okay, and we're integrating that from essentially 0 to epsilon or minus epsilon to 0, doesn't really matter because we're taking absolute values. So basically you're integrating 1 over t. A constant times 1 over t from 0 to epsilon, and that's only integrable if the constant is equal to 0, because the integral of minus of 1 over t is logarithm, which blows up at 0. Okay, so this is finite if and only if 1 minus s is equal to 0, and similarly here, this thing is less than infinity, bounded if and only if minus 1 minus s is equal to 0. Okay, and these two conditions together are not satisfied for any s. Okay, so that means the Dini's test does not apply. Okay, so that doesn't mean that you don't have pointwise convergence. It just means you don't have it by Dini's test. Now, turns out that there's an alternative version of Dini's test, and it sort of makes use of the fact that the Dirichlet. So let's go up here and look at place where I have this written down, which is here. Okay, so this function here is even. So if you apply the function at minus t, it's the same as applying the function at t. And so if you use the evenness of this thing in this formulation of pointwise convergence, you can prove that basically what you do is if you take this function and you break it into its even and odd parts. Okay, so if you have any function f, okay, well, maybe let me write it as g just to make sure that I'm not confusing it with f because it's actually a different function. And if you go, this can be written as g of t plus g of minus t plus 1/2 g of t minus g of minus t. Okay, so this is a decomposition of f or g into this part, which is even, and this part, which is odd. Okay, so this is equal to itself at t and minus t, and this is equal to minus itself at t and minus t. Okay, and so when you sort of if you plug these into this integral, into this integral here, and use the evenness of this, what you can see is that this condition only relies on the even part of the function. Okay, so that gives you, so you can come up with a modified version of Dini's test. Okay, that can sometimes work in cases where Dini's test does not work. So let me tell you what that is. Okay, so there's a even part of Dini's test. Okay, and so here, you can modify Dini's test to look like this. So you go 1/2. So again, you take the even part, okay, of f, okay, plus f of t naught plus t, okay, minus s over t is less than infinity. Okay, so again, what I've done is I've taken the even part, and it's not really the even part because it's only the even part when t naught is equal to 0. But what it is you've taken kind of the even part about t naught. So rather than talking about evenness around 0, you're talking about evenness around t naught. Okay, so but you've replaced f with its even part. But if that's true, then you get convergence of the Fourier series to S. Okay, so this is kind of a modified version of Dini's test. All right. Okay, so let's try that. Okay, and so what I need to do now, so again, I'm going to take t naught equals 0. Okay. And then I'm going to calculate when t naught is equal to 0, this thing. Okay, but, and this is where we see that this business of even and odd pays off in this example, because let's say around t naught equals 0, what is the even part of f? Well, the even part of f is 0 because f is odd. Okay, it's all odd, no even, and so the even part of f is equal to 0. Okay, so since 1/2 f of t naught minus t plus f of t naught plus t is equal to 0. Okay, so I'll call this thing double star with s equals 0. Okay. And so from this, therefore, because this holds with s equals 0, I can infer that the Fourier series converges to 0 at t naught. Okay, so Dini's test doesn't apply, but there's a modification of Dini's test where you just take the even part of the signal, and that does apply. Okay, so therefore I can conclude convergence of the Fourier series to 0. Okay, all right. Let's also try Dirichlet's test. Okay, I'm going to try Dirichlet's test at t naught equals 0. Okay, so to apply Dirichlet's test, I need to check whether these limits exist. Okay, all right, so here's f, and I'm working around 0. So f of t naught plus is the limit of f from the right, which is 1. F of t naught minus is the limit of f from the left, which is -1. Okay, then the derivatives. Okay, well, the derivative from the right is 0, and the derivative from the left is 0. Okay, so those limits all exist. Okay, so we have f of t naught plus is equal to 1. F of t naught minus is equal to -1. F of t naught prime of t naught plus is prime of t naught minus is equal to 0. Okay, so therefore, the Fourier series at t naught equals 0 is equal to the average of 1 plus -1, which is, again, 0, of course. It converges to 0 at one test. It has to be the same for the other one. Okay, all right, so that's one example of pointwise convergence. Oh, sorry. It should be. It should be. Sorry. D. Good. All right, now next function. I'm going to take now this function which I'll call g, and g was the square wave function. Okay. All right, and so this is a half. This is 1. So, okay. So again, g is differentiable except at integer multiples of a half. Okay, and so the Fourier series converges to g at these points. Okay, so at the points where g is differentiable. And I only therefore need to consider the complement of those points, which are the integer multiples of a half. Okay, so at say t naught equals 0, we have, okay, so by Dini's test, so let's see if Dini's test works. Okay, and so and I'm going to go more quickly now through this, but the idea is going to be the same, right? I'm going to take my function and this integral, which needs to be finite, and I'm going to break it up into 2 integrals. Okay, so I have the integral from minus epsilon to 0. Okay, so it's going to be now g of t naught minus t minus s over t plus integral from 0 to epsilon g of t naught minus t minus s over t. Okay, so g of t naught minus t. Okay, so again, so t naught is 0, and so this is g of minus t, where t is negative, so that's g of t where t is positive, and for positive t, g of t is equal to t. Okay, and here, g of t naught minus t is equal to minus t. Okay, and so what I see, okay, so here this is equal to t, here this is equal to minus t, and so if I take s equals 0, then in both cases, when I take absolute values, this integrand is 1, okay, which is integrable. Okay, and so the point is that it works for s equals 0. Okay. And so therefore I can conclude that the Fourier series of G at t naught equals 0. And so, by the way, I've only done these in these examples for t naught equals 0. The analysis is the same for all integer multiples of a half. Okay. Okay. And so I have this other version of Dini's test, but this other version of Dini's test is exactly the same as Dini's test, and the reason is the G is even. You know, F was odd, okay, and so the even version of Dini's test gave us new information here, but here G is already even, and so this modified Dini's test gives us no new information. Okay, good. Now, Dirichlet's test. Okay. Okay, so here I need to check various limits. So I have the limit of f from the right is 0, from the left is 0. The limit of f prime from the right is 1, and slope is 1, and from the left is -1. Okay. All right. So the limits f of the limits exist. So f of 0 plus is equal to 0. F of 0 minus is equal to 0. F prime of 0 plus is equal to 1. And f prime of 0 minus is equal to -1. Okay. And so from Dirichlet's test directly, I have the limit. M goes to infinity. Sorry, these are G's. G is equal to 1/2, and so it's the average of the left and right limits, which are 0. Okay. All right, good. Now, one final example is a new function, and the function I'm going to take is going to be, just get the, so it's going to be H, I'll call it, and it is sine t over 2 square root. All right, so what's this function? So this thing is now periodic with period 2 pi is how I'm going to take this. Okay, we're going to take this thing to be 2 pi periodic. Okay, and so the idea is that it has this value from 0 to 2 pi. And so what does that look like? So if this is 2 pi, you know, so it's really the same thing as sine theta from 0 to pi, because I'm dividing by 2 here. So basically from 0 to 2 pi, you get a lobe of the sine wave, except I'm doing something funny, which is that I'm taking its square root. Okay, so it's the sine function, but square rooted. I'll see why this square root trick is relevant here in a second. Okay, and so then it's 2 pi periodic, so I extend it in the obvious way. Okay. All right, now what does the square root serve to do? Well, what the square root does, so again, let's first of all dispense with the easy bits. H is differentiable at except at integer multiples of 2 pi. Okay, and so the Fourier series for H converges to H at these points. Okay, so it's not differentiable at 0, say, but it's not differentiable just immediately because you can see that the limits of the derivatives from the difference quotients from the left and the right won't agree. But it's even worse than that because the difference quotients actually blow up. Okay, if you think about what the derivative, and that's where the square root comes in here. And so the derivatives, because for t small, let's say, this thing is essentially square root of t, right? Sine t is approximately, or sine t over 2 is approximately t over 2. So you take the square root, and so that's square root of t over 2. The point is that it behaves like root t for t small, and the derivative of root t blows up. Okay, and so the derivatives are actually unbounded as you approach 0 from the left and the right. Okay, but let's apply our tests. Okay, so Dini's test, and so again, I'm going to have to so I need for this thing to be finite. And okay, so let's think about what this is for a moment. And so H of minus t, okay, for t negative is like H for t positive. And so this is approximately, this behaves like root of t over 2, okay, and similarly here. Okay. And so if I choose s equals 0, okay, then what am I going to get here? I'm going to get essentially, right, root t on top, t on the bottom. And so that's going to be like 1 over root t. Okay. And so h of minus t approximately behaves like 1 over, I have this 1 over root 2 factor that's floating around, but then it's 1 over root t. And similarly here, absolute value. Okay, but the point is that unlike 1 over t, 1 over root t is integrable on 0 to epsilon. Okay, and so therefore integrals exist for s equals 0. Okay, and so therefore Dini's test works. Okay, and I get that the limit as n goes to infinity, Dirichlet kernel is equal to 0. Okay, because again, if you take s equals 0 in each of these cases, so when s is equal to 0, you're just looking at this thing, and I've sort of spelled out here that these things go like 1 over root t, and 1 over root t is integrable around 0. Okay, good. So alt Dini, or the alternative Dini's test that I gave, is equal to Dini. Again, since h is even. Okay, and then C, Dirichlet doesn't apply, since f prime of t naught plus and f prime of t naught minus, these limits don't exist. Dirichlet does not apply. Again, Dirichlet's test is only a sufficient condition. This doesn't mean that the Fourier series diverges. It only means that Dirichlet's test doesn't apply. Okay, good. All right, so there's some examples, and so the point of these examples okay, so the tests give conditions on F for convergence of for pointwise convergence. Of its Fourier series. Okay, because nowhere in these checks that I did for all of these functions, nowhere did I ever have to calculate the CDFT of f. Okay, even though the Fourier series involves the Fourier, the CDFT, the values of the CDFT, but nowhere did I have to know what the CDFT was to infer pointwise convergence of the Fourier series. Okay, so let me just emphasize that. So we do not need to compute okay, so conditions like this are what I mean by easily computable conditions, just involving f. Okay. Okay, so as conditions emphasize that a continuity of f is not sufficient for pointwise convergence of the Fourier series. Okay, and so let me just look at the results and point out exactly what I mean there. Okay, so in Dirichlet's test, it's very clear. Continuity would be that these two things agree, and that's not even necessary for pointwise convergence of the Fourier series. But the point is that you need for something involving derivatives to also be involved in the condition. And obviously this corollary is differentiability is sufficient for convergence to F. Okay, and again, and you know, we saw when we proved this that, you know, this difference quotient showed up here, and you can see something very similar here in Dini's test with, you know, this t in the denominator here. You require much more than, you need much more regularity than just continuity in order to ensure that a function divided by t is going to be integrable on an interval containing t equals 0. Okay. And I say that because it's very tempting to say that, you know, just because there's this nice connection between continuity and convergence, it's very tempting to say that convergence of Fourier series is connected with continuity. It's not, although many times people succumb to the temptation. And the other thing I'll say is that all the tests are only sufficient conditions. Sufficient conditions. Okay. And there really are no useful, necessary insufficient conditions. There are certainly better sufficient conditions. Okay, involving, for example, what's known as bounded variation. Okay, and so there's a simple test here known as, if you want to sort of Google it, simple test here known as Jordan's test. Okay. Which gives conditions for pointwise convergence involving what's known as the variation of a signal. Okay. All right, good. So that's pointwise convergence of Fourier series. Next time we will talk about uniform convergence of Fourier series.